Uh, so anyhow, just to refresh in case someone watches this later. Class failed on Tuesday because we couldn't get an internet connection. I blame Comcast. We should sue them because they're criminal. No, I'm just kidding. So anyhow, because of Comcast, we couldn't have class. So I apologize, and then we'll just pick up today. I didn't finish getting all your grades. Some of you will see some of your grades. Some of you will see all of your grades. Some of you, depending on where your name falls in the alphabet, haven't seen maybe just one or two right now. I will fix that today. And then most importantly, I think, Heather, I believe it was you that emailed me about the homework. Look, I only give you guys a due date because of, and I've said this before, the due date is to remind you that if you're doing these homeworks after the due date, then you are most likely working on stuff that we are no longer talking about. We have moved on to new topics. So will I take points off for late assignments? No. Well, okay, let me rephrase that. If your assignment is a day or two or maybe even a week late, I don't care. Now, where you might lose points is if you don't submit any assignments until the last week of class. Then I might say, well, who are you, right? So I don't know if that's clear, but I hope you guys understand that I don't care if the assignment's due tonight at midnight and then you submit it Sunday morning, you're not going to lose points. I'm not going to be mad. What I would hope that you do is that you ask questions, whether it be in here or privately, because it's hard when we're not in person for me to get a gauge of what you guys know and what you don't. Because even some of you will have good work on your exams or homework, but again, I don't necessarily know how much of that is you doing it versus how much of that is maybe you copying it out of a book or off the internet. And not that that's bad to do, but I don't get a good gauge on what your abilities are. It's really hard to get a reading for how we're moving as a class. So anyhow, and I know you guys are busy and stuff too, so maybe you don't have time for all that, but just saying. And then the last announcement I have is a few people have emailed me about my math lab. So my math lab, don't forget, is extra credit. And I'm guessing what a few of the emails said is that some of the assignments aren't visible yet, and I will fix that. I don't know why. We got someone's chatting. I like a good chat. Let's go see. This is like I'm like on the podcast. We have a caller. There's no silly questions. No, it can never hurt yours. So Heather asked the question, can it hurt you? No, absolutely not. So what I usually find is about a third of the class every semester signs up. Nah, you do some, you might even get extra credit. Look, I know that if you look at the technicalities on the syllabus, you have to do like 95% or something. Look, there has been times where I've given people extra credit even if they've only done like half the problems. It's never going to hurt you. It can only help you. Does that make sense? Hopefully. Again, I don't want to force you guys to do it, but it's like anything. If you want to get good at something, you have to do it. And so that's one of my ways of bribing you guys to do work, is offering, well, I guess extra credit and homework is bribery. Here, do the work, we'll give you points. But as some of you know who've ever look, if you've even looked at it, you recognize that there's a ton of problems. It is a big time commitment. But it's not wasted time, in my opinion, because if you do it, then you're going to learn stuff. Of course, unless you pay someone else to do it for you, then you're not going to learn it. Oh, you learn capitalism, I guess. That's a good life lesson. Any other questions about the general course? Don't forget, we're going to have our test. I guess that's a fifth announcement. So exam 2 is next week. So like I told you, you will get it Tuesday after class, and it'll be due Thursday night. So I'll repeat this again. If any of you have a time issue with that, or a schedule conflict, or maybe you're at the beach, or whatever you might have, whatever your issue is, those of you who know me know that I don't actually, a few of you know me, most of you don't actually. I am very willing to work and give you guys the benefit of the doubt, and also work around your schedule. So the only thing is you just have to ask. So, all right, good deal. Okay, so where did we leave off? We left off with a very important topic. So let's switch colors, because let's start green. Here we go. So our last topic was the chain rule. So let's just remind you what the chain rule says. One way of writing it is to use the following. So it's the derivative of the outside function f evaluated at the inside times the derivative of the inside function. So if we can, just do 2 examples underneath just to remind ourselves of the pattern recognition here. All right. So let's suppose we have a composition of this form. Suppose we have 5x squared plus 6x plus 7 to the 8th power. What is this derivative? Well, what you need to recognize is that the 8th power is the outside function, and it's eating the inside function, which is the polynomial inside. So one way to think about this is you bring down the 8 because you're differentiating the outside, and you leave the inside alone. So you just write it right back in. And then it's times the derivative of the inside. Well, what's the derivative of the inside function? It's 10x plus 6. So I'm not going to simplify it. I'll just leave it like this because there's not much else I can do. So if you have a question or a comment about that, please ask. Let's do one more. We'll do it in this dark blue. Okay, so let's look at something like the tangent evaluated at 10x squared. So now the outside function is this tangent. So what's the derivative of tangent? It's secant squared. You leave the inside alone, and then it's times the derivative of the inside, which is 20x. So those are 2 examples of applying the chain rule. So before we go further, let's do a little more of a complicated example. So if you have a question, please ask. All right, so let's do, sometimes we have to do more than one role at a time. So let's look at a problem like that. So let's suppose that we have to take the derivative of the square root I'll say x squared e to the 5x. So this is a little more complicated of an example, because if you ponder what you're looking at right now, you have the square root function, which is eating something. Now the square root function is eating a product, which means if we look at this, we're going to have to apply first the chain rule, and then we're going to have to apply the product rule. So, and remember how this works. The chain rule basically tells us that the derivative operator, it works from the outside in. So the way you need to think about this is, what's the derivative of the square root? Well, one way to ponder it is it's 1 over 2 times the square root, and then whatever's inside. And then it's times the derivative of what's inside. So we're going to write it like this for now. We're going to go one step at a time. Because right now, to take the derivative of the quote-unquote inside function, we're going to have to rely on another friend, the product rule. So I'm going to leave this first piece alone because it's already done. And so now the product rule says it's the derivative of the first times the second plus the first times the derivative of the second, which is 5 e to the 5x. So this is the derivative. Now, I guess we could simplify it a little bit, but maybe we will, just so we get some practice. While I'm erasing this period, does anybody have a question? So one of the things I can do is I note I have an x e to the 5x. So one way I might write this is I might write this x e to the 5x, and then I have a 2 over this. And then what's left over is a 2 plus 5x. So perhaps I write my I write it like that. So just to give you an idea of what logic and what I'm following here, the steps. This up here, what I did is I applied the chain rule. Then I used the product rule. And then I was done with the calculus aspect. The last step was me just rewriting. Now, what I mean by that is that last step is technically unnecessary. All I did was rewrite what I like the expression to look like. If this were a homework question, or this were an exam question, and all I asked you to do is compute the derivative, then you could stop right here at the second step. That is the derivative. I just wanted to write it in a little more compact form. Does anybody have a question about that? All right, so okay. So now we got to get into some cool consequences of the chain rule. So the first thing we're going to talk about is what's called implicit differentiation. Man, I'll tell you what, gang, I am losing my mind. I cannot spell. Spell it out. What is that? What's like your 5th grade teacher says? Spell it out. Differentiation. That's a T. Ation. Okay, so here's Here's the way I like to think about this, which is a little different than how most books do it. So maybe the books are confusing and I'm not, or maybe I'm confusing and the books aren't confusing, or Khan Academy or the internet, or wherever you go to get your resources. Here's the way I like to think about it. So, and perhaps what happens as students is we're so worried about, is this the right answer, or what formula do I use, or what pattern do I follow, that we sometimes lose sight of the bigger, deeper picture, what's really happening. And so if you think about what's really happening, let's recall something. So recall, the derivative is defined as the rate of change. So if we think of the English of it, it's defined as the rate of change of, or in the following way. So if we write it like this, when we write something like df dx, this means what happens to f of x when x changes. So another way of thinking about it, if you use different language, what happens to the output when the input changes? Or another way, what happens to the dependent variable when the independent variable changes? So another way of thinking about it is the letters matter. So I never see books do it this way, but I think this is a good way to grasp something. And again, if it's confusing to you, that's okay. Look, this kind of stuff we're going to do is going to be confusing to anybody. Even the best students struggle to learn this. I struggled. Everybody struggles to deal with the chain rule and the implicit diff. It's just hard stuff to learn. So every time you get discouraged, remind yourself, this is hard stuff to learn. And then just be happy that it's 2020 and you can go on the internet and you can do all this stuff on your phone for free, whereas 25, 30 years ago, you'd have to go to a library and read through dusty old books. And now you have pretty videos that everybody animates and it's all over YouTube. All right, so here's what I mean by the letters matter. Let's look at a simple example. If I write d dx of x squared, we know that this is 2x. If I write d dt of, say, t to the 5th, then hopefully you guys understand this means 5t to the 4th. Now, if I write d dx of y, what does this mean? So let me repeat this because I hope you spend some time thinking about it, and you might not. You might hate me. You might say, oh, Grady, I hate you. You don't update our homework grades. You're the worst ever, blah, blah, blah. These are things you probably get mad about, and I feel you. And I apologize. But say even if you do hate me, maybe just for your own personal glory, you say, I'm going to understand what this babbling man in his kid's playroom behind him is babbling. Or maybe you're all sleeping for all I know. Okay, so if you remember the definition of the derivative, it is the limit as h goes to 0 of that difference quotient. So if you think about it, the numerator, the difference quotient, was looking at the two outputs. Or if you want to think about it, it was looking at the dependent variable. And then you're dividing it by the independent variable or the input changing. And so that means if you have a function f of x equals x squared, then the derivative depends on the variable x. And if your function is in the variable t, then the derivative depends on t. But you'll notice in this last example that I have written here, what this means is that the independent variable here is x, but I don't see the independent variable in my expression. So this can mean two things. So let's be very clear about this. So the first thing it could mean is it can mean 0. And why might it mean 0? Well, we'll say that in a second. And what can it mean otherwise? Well, otherwise, it could just mean y prime or dy dx. So let's think about why both of those could be correct. Well, the reason the first scenario could be correct is we know that the derivative of a constant is always 0. So what we're saying is if the output never changes, when the input changes, then the derivative has to be 0. However, the second scenario can be correct as well, because how do we know that y doesn't depend on x somehow? So let's go to the next page and let's write this out more specifically. So if y is representing some unknown number, then the derivative of y with respect to x, this makes sense. And again, the reason for that is because the derivative of a constant is 0. However, if y depends on x somehow, then d dx of y should mean, dy dx or y prime, whatever notation you want to use. So what we're imagining here now is that there's two scenarios that can occur, and context is key. It depends on what context we are in. So if we go back to this page and look at this, I want to do a similar thing now, only I want to write it slightly different. And for me, this is when this all connected. Somehow I figured to write it this way, and it made sense to me. So therefore, by the chain rule, if y depends on x, so how do we write down, what is the symbol for that? We usually say y of x. If y depends on x, we use this sort of notation so that you, the reader, knows that y depends on whatever x is. So let's look at some simple formulas. What would d dx of y squared be? Well, the chain rule tells us this would be 2y times dy dx. What would the derivative of y cubed be? Well, the chain rule says it would be 3y squared times dy dx. And then just for good measure, let's do something else. How about the sine of y? Well, what's the derivative of sine? The derivative of sine is cosine of y times dy dx. So the key observation here is to note what is the independent and what is the dependent variable. And this is often a jump for us because so often we don't have enough experience at our level when we're in calculus 1 to really have a solid understanding of this. So it's going to take some time for you to understand why I'm not just writing formulas for the sake of writing formulas, that these things actually have meaning. Does anybody have a comment or a question? Any questions, comments? Okay, so what this tells us, what the chain rule does, is this gives us an amazing sort of interesting thing that we can do. So if you think about the definition of the derivative, it only made sense for a function. But with the chain rule, we now have the power to not just look at how functions behave, but we can also look at how equations that relate two or more variables behave. And this is a very, very important tool in actual math, engineering, and science. It's phenomenal. And the reason that it's an important tool is because not everything is a function. You guys are aware of this, at least you were taught this in an algebra class, for example. So let me sort of explain what I mean by that. So this fact allows us to not just analyze functions, but also equations. So again, you're probably thinking, what is he even remotely talking about? Well, here's what I mean by that. So the standard example that you guys would have talked about, and if you put your time machines on, at one point you were in a math class and some instructor was talking about the vertical line test, and this is the graph of a function, and this is not the graph of the function, and stuff like that. So why did I say this fact allows us to not just analyze functions, but also equations? So here's the famous example. A circle. So the circle of radius 1 at the origin, or I shouldn't say at the origin, centered at the origin. So we can quantify this. It has an equation. It's x squared plus y squared equals 1. If you look at all points that satisfy this equation, they make a circle. It's called the unit circle. Radius 1, center at the origin. Now, you would think that we should be able to analyze a circle. What's the tangent line at any given point? Blah, blah, blah. However, with our current definition of the derivative, it doesn't apply to this because this is not a function. So here's an important fact that you need to note. Note, there is no function of one variable whose graph is a circle. So another way of thinking about that is if I said to you, can you solve that for y? And the answer is Yes, you can solve it for y, but you don't get a function. So if you solve for y, you get two functions. So if you solve for y, what do you get? Let's go real slow. If I solve for y, I have y squared is 1 minus x squared. And then if I have, take the square root, I get y equals plus or minus the square root. So this is two functions. I have a top and a bottom. And if you go and play around with this on your calculator, which I think is a good thing for us to do right now, so I will do it. And I will show you. So if I go to Desmos, let's get Desmos here. You guys see Desmos? I hope you all do. If I graph x squared plus y squared equals 1, I get a circle. Nice red circle. Now, if I want to graph the circle using functions, not an equation, so there's a difference between a function of one variable and an equation. And so if I draw y equals the square root, just like we solved, of 1 minus x squared, what you'll notice is I get the top half of the circle. And then if I go and do the negative square root, the other solution, you'll see I get the bottom half of the circle. So in order to construct a circle using functions, I need two functions. Or I can use one equation. So these are probably ideas you've never thought about before, but they're worth spending some time pondering them now. Ooh, that's a big word, pondering. You can go sit in your room and be pensive over this. These are like SAT words, or as I like to call them, wealth test words. Anyhow, so again, what we understand when we're doing math for fun, or if we're doing math for applications, whether it's physics or engineering, and what, like when I say we, I mean professionals, and what you as amateurs might not understand yet is oftentimes in the real world, we can't get functions. We can only get equations. And so the nice thing is this chain rule gives us what's called implicit differentiation. And implicit differentiation says we can analyze equations almost the same way we analyze functions. If you have a question, please ask. And let's see how all this works. Let's do some computations. Okay, so we're going to do a calculation, and there's no reason to believe it's a legal calculation except for the fact that I'm telling you there's a big theorem in math called the implicit function theorem. And what it tells us, and that's, you study that kind of thing in like way higher classes, graduate level courses, but it's real important. And one of its consequences is we get to do this thing for legally. So here's an example. So first, we're just going to do the computation and we're going to explain it. So I start with x squared plus y squared equals 1. And then what I'm going to do is I am going to take the derivative of both sides. So if two things are said to be equal, it seems logical that their derivatives should be equal, whatever that means. And then on the left-hand side, we know that the derivative, we can do each piece at a time. So this is the derivative of x squared plus the derivative of y squared. And of course, on the right-hand side, we know it's 0 because the derivative of any constant is 0. And then we have a derivative here, which is standard. It's 2x. But now here, we have to be more creative. We are going to pretend, and this is not really pretending because we know that y and x are related. We see they're related. They're related by x squared plus y squared equals 1. So if we want to ask how y changes when x changes, we have to note that the chain rule says that this is 2y times dy dx. So what we've done is we started with a relationship between two variables, x and y. And what we've done using the chain rule is we've come up with an equation that relates the change of y in terms of x. How does x and y, how are their changes related? Well, we see that. We have an algebraic equation now at the bottom. So you can solve this. This equation can be solved for dy dx. And so if you do that, if you take dy dx and solve it, you get the following. You take 2x to the other side, it becomes negative. You divide by y, and what you get is you get negative x over y. So that is telling us how y and x, their change is related. So if x changes, this is how y changes. And if you look at the picture of the circle and you look at this dy dx equals negative x over y nonsense, you'll start to see that some obvious things are true. So if we go back to our picture of Desmos for a second, notice what is, if I put the point 0, 1 there, this point, notice what's the tangent line here? The tangent line is nothing more than the line y equals 1. And what is the slope of that line? Well, the slope of that line is, of course, 0 because it's a horizontal line. And so if we go back to our whiteboard, notice if I set x equal to 0 and y equal to 1, dy dx becomes, in the red equation, if I set x equal to 0 and y equal to 1, so the point 0, 1, then the slope is 0, as we expect. So let's study this for a second so we can see. So set x equal to 0, y equal to 1, and when you do that, you get dy dx equals 0. And so what does this mean geometrically? This means as we know already, that this means the tangent line has slope 0 at 0, 1. So let's do another point that's on the circle, and that's not such a trivial one. So maybe you guys know this, maybe you don't. I don't know, but so the point, okay, so I don't know what's the best way to think about you know, getting you guys to do this. But one point, and if you know basic trig, this is obvious, but maybe you either do or you don't. So here's a point that we want to check out. So let's change colors. We'll go with green. So set x equal to 1 over the square root of 2 and y equal to 1 over the square root of 2. And then in this particular scenario, what is dy dx? It just becomes -1. So this means, and this is not obvious, so I wouldn't say as we know. So this means the tangent line at 1 over root 2 comma 1 over root 2 has slope equal to -1. So if we go back to Desmos, we can see this quite easily. So I'll do that in a second. I'm just gonna. So I'm going to take you to Desmos. So right now you should see Desmos, and you should see a blue line that's tangent at the 1 over root 2, 1 over root 2. Its slope is -1, as you can see. So I hope, I don't know if it's the right thing to do, but I do hope that you guys spend some time thinking about this example. One of the things that I just think is a bad idea is too often students just get bogged down in just trying to solve problems, and you don't really think about the problem. You're just trying to be some little poor excuse for a robot who systematically solves something just to get, is this the answer? Is this the answer? And I know that's not your fault, because that's how schools are set up. Everybody wants to test you and do all that. But I can't emphasize enough how important I think it is, if you want to learn, to study examples like this and think about it. What I'm writing, why am I saying what I'm saying? All that kind of stuff. So that is my advice to you. Will you take it? I don't know. I hope you will. Okay, so let's move back. Anybody chatting? I don't hear anybody chatting. Good deal. Okay, so any questions, comments? So let's do another, a couple things. So first off, why do we call this implicit differentiation? Well, because one variable depends on the other implicitly. And maybe you like, I don't know what that word means. Well, let's think of it from the other side. So compare this to explicit dependence. So I'll explain that on the next page. But we're using two English words here, and they're very much being used as their colloquial English meaning, implicitly and explicitly. So I want you to think about this, and then we'll do a couple more examples, and then we'll show you all the power that this has. By the way, it should be pointed out while you're writing this down that This big yapping theorem I talked about, the implicit function theorem, as I said before, it is used in high-level math, science, and engineering all the time. I mean, much of my thesis for my PhD was relying on that theorem. So it's not just a bunch of symbolic gibberish that we ask, you know, first-year calculus students to do. Okay, so let's really look at what this explicit and implicit nonsense means. So x squared plus y squared, you know, y depends on x implicitly. But if I have something like y equals 3x squared plus 5x, then y depends explicitly. So a good way to think about this is, can you or can you not solve for y in terms of x? So if you want to break it down into that sort of argument, I would encourage you to do that. So if we separate this a little bit and let's use another color here. Let's use green. You can't solve for y in terms of x. You can't. And what I mean by that, I mean that you can't get one expression. We saw that you can solve for y, but you get two expressions. Here, you can. So I hope you'll think about that, and then you'll start to recognize what's happening here. All right, let's do an example or two. Actually, I'll go back and give you a moment to see if anybody has a question or a comment. Anybody want to yell? We haven't lost the feed yet, so that's good. Okay, so let's switch colors here. Let's do an example. So determine y prime, which is, by the way, sometimes you guys get confused. That's the same thing as dy dx. Let's do this one. So this will be our first example. So I want to determine my derivative here, dy dx. Okay, so what do I want to do? So the first thing I have to do is I have to differentiate both sides. So one way to think about that is to take d dx, take the derivative of both sides. So we'll skip a step and we'll start by writing each piece out. And so this derivative is easy, it's just 1. This derivative is similarly easy, it's 2y prime. Now, we have to be a little careful on the right-hand side. So the chain rule tells us this is 1 over 2 times the square root of y times y prime. So this one is a bit of, you're going to have to maybe take a moment and and even scribble down and do it yourself to convince yourself, okay, I'm cool with this. Whew, how much fun are we having? Scale of 1 to 10. Is anybody alive? We know Heather was alive at one point because she chimed in. So let's see who we have on here. We have Elijah, Emily, Michael, Leanna, Heather. I think I'm saying that right. I probably mess your names up. Cammie. Oh, Cammie, you sent me an email. I got to respond. I think that was about my math lab. That's good. And then, is it Bo or Bay? See, this is what sucks about not being in person. I want to be able to discuss life with you guys. We're missing out on so many. You guys are missing out on all the insanity that I bring. Anyhow, can you hear my kids up there, by the way? They're going nuts. I hope they're not killing one another. All right. Sweet. Okay, so we're not done yet. All we did was take the derivative. So our job is to determine y prime. So we need to solve for it. So we have this is an algebraic equation now where the unknown is what we want to find is y prime. So we need to be able to solve for it. So this is now like an algebra problem. So what one way you can do this is you can. So let's slow down. That way you can have something to read. Let's take our time. So what does there left to do? So it remains to solve for y prime. So we'll do that on the next page, if you bear with me. So if you, by the way, I shouldn't go so quick because we have 1 plus 2y prime equals that gibberish. So let's just rewrite it again. So how would I reason this? Well, I have to get everything with y prime on one side. So I'll do 2y prime minus 1 over 2 root y prime. And then I'll take the 1 goes to the other side, so it becomes negative 1. So the first thing I'm doing, if you're keeping score at home, is I need to, just think of this as an algebraic equation. So I need to, what I'm doing, one way to think about this is I am going to combine like terms. So how am I going to do that? Well, I'm going to factor out the y prime, and then I'm left with 2 minus 1 over 2 root y. The quantity is negative 1. And then this is the scary thing. I know, this is basic algebra, but it just looks a lot worse. Now I'm going to divide both sides by this creature. So that is one way to do this. It's an ugly way of doing it. I could even rewrite this if I wanted to because it looks sloppy. Maybe we should do that for good practice. Does anybody have a question about this? If I just got up and walked away, how long would you guys last? That's a good question. We should do that one day. We'll play a game. We'll do like a study on the Zoom lectures. How long will they last? Who would call the police? That's true, but Heather, that's why I sent you guys that message right away, because I didn't want you guys to stick around. That would have been unfair to you. You guys have lives and stuff. You don't need to wait for me to figure out my internet connection. That's disrespectful. Can you imagine but some people would have wanted you to stick around until they figured it out, but that's not fair. All right, so the last thing I'm going to do, this is done. This is okay. So let's also sort of tell you what we did at each step, so in case you're interested. Because I know the first thing you're going to do on a Friday night is go over these notes, because that's what all people do. So here I factored out y prime, and then here I divide to isolate y prime. Okay, so just for fun, what I would do is I would rewrite this. I don't like the way that looks. It looks very, all those fractions are mentally boggling on my brain. So I'm going to do a trick to make it look prettier. I'm going to do the old multiply by 1 trick. So even though this is good, I'd like to make it look prettier. So the last line is correct. However, I like to just use the word however. However, let's rewrite to make it, I'm going to write prettier, but this is so mean because people don't like when you do that because they say that's offensive or something. I don't know. Let's use it in the O'Grady meaning of math. So if you remember what this thing was, it's quite ugly. It's -1 over this ugly thing. So we had y prime is -1 over, what was it, 2 minus 1 over 2 root y, like this. So I'm going to give you a little trick. Let me just double check that. Yeah. I'm going to give you a little trick. When you have something like this, you can sort of remove the ugliness if you do this old multiply by 1 trick. So I'm going to multiply the top and the bottom by this. And so when I do that upstairs, I get -2 root y. And then downstairs, if I distribute, I get 4 root y minus 1. Now, I guess prettier, the reason I wrote it in quotations is because it's in the eye of the beholder. And I can even do one better. I don't like that minus sign. Get rid of it. How do I get rid of it? I take it downstairs and I can write this like this. So to me, in my own personal opinion, this is more aesthetically pleasing. That's another big word, aesthetics. We're on the ball today. See, you get an all well-rounded education. And then you got a backhanded compliment / you now know O'Grady hates standardized tests because he called them wealth test. See how I do these things? All right. You don't have to do this, but I thought it's a neat trick to show you because I'll tell you what, I prefer this expression of y prime to the other one, but that's just me. But then again, I guess part of my job is to do these things. Any questions, comments? All right. We're running out of slides. So I sent, this is a cute thing. I sent an email. Hold on a second. What do you mean by the 2 terms? Where did I say that? Are you talking about with the circle thing? I don't remember. Yeah, okay. So if you're talking about that we go all the way back here. What I mean by 2 terms, it's no, not always. I mean, look at this one. You can't get anything. Give an example. Look at this equation right here. This equation right here, it is impossible for you to solve for y. You're not even going to be able to get 10 versions. How are you going to get y isolated? Now, in the circle example, all you had to do was, since there was only y showed up once, you can just take everything to the other side and take a square root. But here you have y showing up in 2 different ways. It's in a square root and it's multiplied by 2. There's no way that you can even remotely begin to solve for y. It's impossible. Does that make sense? So what happens in the real world, and not real world, I'm saying, what often happens in most cases, most things aren't as simple. Circle's a very simple equation. But if you look at examples in books of implicit diff, and the equations we find in the real world are usually very, very complicated. You couldn't even begin to figure out how you're going to solve for one variable. So this is why this tool is so useful. Because if you think about what's happening, we know that this equation, or I don't say we know, I know, but this equation represents some curve in the XY plane. And what's interesting is this curve cannot be generated by any function. The only way it can be generated is by all the x's and y's that satisfy this. And what's quite fascinating about that is implicit diff is very magical in that it gives us a way of studying the geometry of this curve, meaning like how steep it is, even though theoretically we can't graph this curve. So if I can change, if I go to Desmos, Desmos is very, very good. It can graph this thing. So here's what the graph of it looks like. Notice it has, this is clearly not the graph of a function, right? Because it fails the vertical line test. But look at this curve. So being that we found the derivative, we can now tell you how steep this curve is at any point. We can find the tangent line. We can analyze all kinds of things. Like if you take higher level classes, you talk about these things called curvature, where you think about think about when you're driving down the highway. You guys know that certain roads you can't drive fast on because if they're sharp curves, it's dangerous. And so one of the things we measure is what's called curvature. And that has to do with derivatives and all kinds of stuff. And so these kinds of ideas, the fact that implicit diff allows us to analyze this curve is very, very useful. Like I could say to you, give me the tangent line at a given point. So maybe I'm gone off topic a little bit. If I did, I'm sorry, Heather. But the point, I think the question is, you asked about the two terms thing. So you're asking about a specific example in the circle. And in the circle, we can solve for y, but we don't get an explicit thing. We get two different things. But in general, there's nothing that says we can even remotely begin to solve for y, especially in an equation like this. This is a very complex equation. So anyhow, think about this stuff if you want to. If not, just learn how to do the problems via me or YouTube or Wolfram or whatever internet source you want. It's up to you. But I encourage you to learn this stuff. Okay. Now, implicit diff doesn't just end here. It does a heck of a lot more. So let's talk about a few of these things. Very good. So here we go. So implicit diff opens tons of doors. For example, we can now readily compute the derivative of inverse functions. So let's just show you an example how it works. So why would we care about this? Well, we know lots of inverses. For example, we know the derivative of e to the x, but we don't know the derivative of its inverse, log. We know the derivative of the sine and cosine, but do we know the derivative of the inverse sine and cosine? And so what's extremely useful is that implicit diff holds the key to this. So essentially, we are now going to get a whole crap ton. Should I use that word, crap ton? We're going to get a ton of formulas, easy and cheap. And these are important formulas that are used all the time. So let's illustrate with an example. Here we go. Oh, by the way, I cheated you guys out of another example. I said I was going to do 2. Did I say that? Did I cheat you guys? And that's what everybody yelled about on the test. They said, we need more examples. Obviously, I did 1. We'll have to do another one. But this is, in fact, an example. This is the same idea. All right, so let's look at what is the derivative of the natural log? So if I said to you, compute this derivative using the definition, your head would explode because you'd be like, huh? How do I even do that? Limit x goes, or h goes to 0, that'd be insanity. So here's the trick. So note, if y equals log of x, then e to the y equals x. So that is the inverse relationship. That's what it means to be inverses. All right, so what use is that? Well, now we've eliminated the unknown. The unknown thing was this log x. We didn't know how to differentiate that. But what we do is we now have an expression we do know how to differentiate. And so this is extremely useful. So we can differentiate this now. So if we use implicit diff, here's what we obtain. We have e to the y equals x. So implicit diff says take the derivative of both sides. Now the derivative on the left-hand side is going to use the chain rule because it's e of y. So this becomes e to the power y times y prime. That's the chain rule. And the one on the right is just 1. So again, I'm using the chain rule because look at the letters. If you look at the letters where my cursor's moving here, what the heck? How's this work? So if you look at this right here, oh my God, I ruined it. What is happening? So the letters do not match, so to speak. If you look at this right here, that x and this y are not the same letter. So that means implicit diff applies. So we have this relationship. And then just like before, we can solve for y prime because that's really what we're after. We're after y prime. Remember, y is the log of x, so that's what we're after. All right, so how do we solve for y prime? Well, y prime becomes 1 over e to the y. We divide both sides by it. But if we sub back in what everything is, what is y prime? Well, y prime is just the derivative of the log because that's the derivative of y, which is log. And what is e to the y? Well, e to the y by definition is x. So this just becomes 1 over x. So let me annotate each line with what we did. So let's be very clear. What is the top line? This is just our definition. So this is the inverse relationship. This is implicit diff. Which also means this is implicit diff. This line we just solved for y prime. And then down here, we replace y with x. Now, I guess I should be a little more clear because I'm not replacing. Let's say replace y, or excuse me. Let me be very clear so I'm not confusing you. So what am I replacing here? I'm replacing y prime with d dx of log and e to the y with x. So why would I replace e to the y with x? Well, that's what it is. Look up here. E to the y and x are the same thing. So now we have this simple and beautiful formula that the derivative of the natural log is 1 over x. So this is something you just need to know. The derivative of a log of x is 1 over x. So this argument that we used is extremely useful. It can be used on any inverse relationship. And actually, it has a name. It's called the inverse function theorem. Not that you need to know that. But it can be used. So a similar argument can derive lots of new identities. So you should do this. So for example, you can show that the derivative of the arc sine or the inverse sine is 1 over this square root. It's a very useful relationship. The inverse cosine, the arc cosine, is this relationship. And the inverse tangent, or the arctan, however you want to call it, has this derivative. So these are 3 very, very important formulas, and you could do any inverse function for that matter. So these are formulas that you should know if you're a calculus student, whether it's in Calc 1 or Calc 2 or any classes that are in math that go beyond this. These are formulas that will pop up over and over again. They pop up in physics and engineering courses all the time. Know them. Does anybody have a question? All right, so let's run a Blackboard space. Oh yeah, that's what I was going to tell you. It was funny. Before I got interrupted earlier, I went on like a chat or whatever with the Zoom people, and I said, they only give us 19 boards. I'm sorry, they give us 20 boards. And I said, why are there only 20 boards per Zoom session? And they said, if you have to write more than 20 boards, you're going to bore your audience. And I said, that's a good point. So this is our last board. Let's do a couple examples that are very important. So let's compute the derivative of, say, the natural log of 3x squared. So this is a composition. So I have to use the chain rule. The natural log's derivative is 1 over what's inside, so 1 over 3x squared, times the derivative of what's inside, which is 6x. And of course, you could simplify this if you wanted, but you don't have to. Let's do one with the arctan. How about the arctan of 5x? So what's the derivative of the arctan of 5x? Well, the derivative of the arctan on the previous page is 1 over 1 plus input squared. So we'll put it like this. And then it's times the derivative of what's inside, which is 5. Any questions about these creatures? Here's a good one. Let's take the derivative of the natural log of the square root of x squared plus 1. This is going to require some skills. So it's 1 over what's inside times the derivative of what's inside. So let's go slow with this one because this is another chain rule. So this guy looks like this. So what's the derivative of this? Well, we know it's 1 over 2 times the square root of what's inside. And then it's times the derivative of what's inside, which is 2x. So that is an ugly problem, but it is one that you're all capable of doing, and you should build to these things. Does anybody have a question about these things or anything? Homework problems? Comments, questions, concerns? I mean, this stuff comes down to practice. There's two things you can do. You can learn to do it yourself and use the internet to check your answer or the books to check your answer. Or you can just use the internet to get the answer and then you don't learn anything. You might get 9 or 10 points on a homework, but you don't really learn anything. So I hope you guys use your resources to help you learn, but I can't force you to do that. So anybody have a question or a comment? So I'm assuming on your minds, like what kind of questions are going to be asked on the test? Well, stuff like this. Can you compute derivatives? Can you find tangent lines? All that kind of stuff. Yeah, so that's a good question, Michael. What sections will be covered on the exam? I mean, we're going to cover up through chapter 3. So perhaps 4.1, depending on how far we cover. So if you look at the book, the books we use what? The chapter or section 311 in the book is what's called related rates. We didn't talk about that yet. We will. I just do it in a different order than the book does. So you can imagine that we'll probably cover up through 4.1 or 4.2. It just depends on how far we get on. I'll have a better answer for you on Tuesday. Maybe 4.1 at the most. Now, if you asking about like, should you practice problems in section 2.6, am I going to ask you limit questions? It's possible, but they would be in, everything's going to sort of be in terms of what we've been doing since the last test. Now, that being said, a limit could pop up because I might, who knows, but it's kind of hard to say. I mean, you need, it's cumulative in the sense that you can't do these problems unless you know the other stuff. But I'm not going to probably ask you to compute a limit that you would have been on the last test. I might ask you to do some, I don't know, maybe, I don't know. All questions that you're going to see on this test are going to come from chapter 3 or possibly 4.1. All right. Does anybody else have any questions? Yes, Heather, I will do that. I will make more my math lab. And I think someone emailed me about being able to register. So I'll open that back up. It's usually closes, but I can open that for you. So if anybody wants to register, you might even be able to cheat the system. I think they let you register for free for like a couple weeks. So if you time it right, you can get the free version up until the end of the semester. Any other comments or questions? All right, well then I thank you. I appreciate you guys joining. Hopefully you learned. Hopefully you'll go learn more. And I will speak to you all on Tuesday, if not sooner. And don't forget, as your grades get updated, if you want to meet and talk about anything, please let me know. And when I say meet, I guess that means on Zoom. So, all right, everybody, have a good day, and thank you for joining. I will talk to you soon.